Welcome to the third part of this tutorial, Advanced Chemical Kinetics. Now we're going to look at how we can derive the integrated form of zero order and first order reaction. Let's start with zero order reaction. As we discussed in our previous tutorial, for zero order reaction, the concentration of the reactant is raised to power 0. So if this is an equation, and write R equal to K negative A raised to power 0. That is zero order reaction. Also, we can now, this one can be expressed as dA, that the rate, the change in function of A over the change in time. Change in the function of A over change in time equal to minus K A to the power 0. So these are and these are the same thing. So having done that, we know that in mathematics, when a number is raised to power 0 is equivalent to 1. So this will vanish. We now have dA equal to minus K dt, crossing this one to the other side. Then integrating this equation with boundaries. We now have integral of dA, taking the function of A as at at time t, and then taking it as a0 at time 0, equal to minus k integrating dt, taking time to be equal to t, which corresponds to the concentration, and taking time to be equal to 0, which corresponds to the concentration at 0. If I integrate this, I'll now have a boundary at and a0 equal to minus k then t, that is it. If I substitute here, I have at concentration at time t minus concentration of A at time 0 equal to minus kt. So if I swap, I will still have minus a0, that is putting this one in front, plus at, that is it. So equal to minus kt, making k the subject, or minus k the subject. Minus k becomes equal to negative a0 plus at all over t. Multiplying both sides by minus 1, I have k equal to a0 minus at all over t. Multiply both sides by minus 1. Minus 1 times this will be plus. Then minus 1 here, open the bracket, is plus, it turns to minus. So that is it. That is the formula for obtaining the rate constant for zero order reaction. This is the concentration at time 0, this is the concentration of time t, and this is the time of the reaction. Let's now look at an experimental data to apply this. Let's say we are given this with this equation, whereby we have time in minutes, we have concentration in mole per dA cube for a zero order reaction, 150 for 0, 5, 142.7. When time is 10, I have concentration as 1 at 5.4. When time is 15 minutes, I have 128.1. Is 15, I have 128.1. When time is 20 minutes, we have 120.8. When time is 35 minutes, we have 113.5. When time is 30 minutes, we have 106.2. We are asked to obtain the rate constant, the value of k, for the above zero order reaction. So if you look at this question, already we have been told that the reaction is zero order, and we are now told to obtain the value of k. We look at the derived equation for the rate constant and apply it. So how do we go about it? We seek the equation about since we need it. So write it up. A constant of A minus AT over time. So going to the time is 0 here. Let's go to the second. We use the second set when the time is not 0. So we say when the time is 5 seconds, the value of K becomes the initial concentration now, which is 150 AO at time 0, minus the concentration at time when the time is 5 seconds is 142.7. We substitute. All over the time is 5 seconds. Repeat the second one when the time is 10 seconds. How to get our K? We still go back. When the time is 10 seconds, like this one, the concentration of the initial concentration remains 150 constant, and the concentration at time being 10 seconds is 135.4 over 5. So we also do the third one when the time is 15 minutes, not seconds, minutes, 5 minutes, 10 minutes, 15 minutes. So the unit being there is minutes. So our K becomes, we now use the initial concentration, which is 150 up here, and then the concentration at time of 10 minutes or 15 minutes is 128.1 over 15. So when we solve it, we'll be getting 1.46 per minute. 1.46 per minute in each case. So we see that if you continue to do the fourth one, fifth one, and sixth one, see the same value 1.46 by substituting their actual or appropriate values. That means that this reaction, which is in agreement, the data is in agreement with the zero order equation, giving us the same value for the rate constant, is a zero order reaction because of the consistency of the values we have obtained. So remain tuned, subscribe to this video, and continue to watch as we move to the first order kinetics. Thank you.